On Wednesday, so I'm planning for the class to be review. It seems that one of the things you all had the kind of the most challenge with was interpreting PCA and SUD. So I'll plan to prepare at least some amount of stuff on that. But I'm open to what I should do with the rest of the lecture time on Wednesday. If there aren't any specific suggestions, the plan would probably to go look at the practice exam, which is posted on the class website, and work through some projects on there. But if there's anything else specific that people would like to see or need to do in the lecture, so if you let me know now, I can be prepared for that.
Yeah. Question. Does the practice exam have answers on the website?
So I think I don't have them linked off the website. I think someone linked them on Canvas earlier. I think a previous iteration of the course, there were some answers provided and they're linked off of the Canvas page someplace. So does anyone remember if that's true or not? If I have them, I think they're up there. Otherwise, I don't have the answers. I don't think I have them prepared. I thought I forgot that I have them, and then someone found them someplace. They are linked off an old version of them on the class website. So okay. So if you think of something you want me specifically to go over on Wednesday, I can do that. Otherwise, it'll be a review and stuff. Yeah.
Will Wednesday be recorded?
Yeah.
Okay.
Yeah. So so I plan to record that. Yeah. And then so let's see. So the final will be December 12th, Thursday, December 12th. That's Thursday of next week at 3:30 for 2 hours. It should be in this room. If anything, if I'm like 90% sure that's right, I'll double check, and if it's different than that, I will make sure to post on Canvas. What?
What is that?
So it's as described on the course webpage. Thursday, December 12th. That's Thursday of next week at 3:30 p.m. in here. Okay, and so that exam is going to be 2 hours. So, and we've had the fourth quiz will be today. We'll have had 4 quizzes. Each of those are half an hour. So, good thing to expect. It'll kind of be like 4 quizzes all stuck together in one. Okay. And hopefully roughly the same amount of challenge. You're going to get either 4 one-sided sheets of paper or 2 two-sided sheets of paper. So you can, if you want to use the same notes you did for the quizzes, that's fine. If you want to re-engineer them, that's fine. But so it should really be like 4 quizzes just stuck together. Yeah.
I couldn't remember if this is okay or not. Are we able to type and like write them out, or?
Yeah, it can be any way you want to do it. In fact, you know what? I'm fine if you want to share the notes with each other. That's totally fine if you work together on them. Like in the past, I let people print out anything they wanted on paper, but then people were bringing in hundreds of pages of paper from the book, and I decided that wasn't a good thing either. So I mean, the point is, I don't want you to have to just memorize everything, but if you don't know what it means ahead of time, you're gonna be in trouble, right? So to write down anything that you might think is useful. It should follow. If you look on the webpage, for every kind of line, I've got the chapter numbers in the book. And it pretty closely follows those kind of what we've covered in those chapters in the book, right? So you kind of that narrows down what we covered in the class, but that's what it should be about. And again, I'll try to ask you kind of the core things I really want you to learn from the class. not things that are more, not esoteric, but things that are kind of pushing the boundaries of what I think you guys can really comprehend over the course of the semester. Right, so I'll try and test you on the really core ideas. They should be things you don't need to do a lot of calculations. If you do them, they should be very, very, very easy. You won't have to write the code or anything like that. But you should be able to interpret algorithms, maybe run a very simple version in pen and paper with kind of drawing pictures and stuff like that. Okay. Also, homework 5 has been posted. It is due this week on Friday. Okay, so Friday at like midnight or so. The previous things in the class, I told you one deadline, and then Canvas marked it late, like 4 or 5 minutes later than that. And I assigned late grades based on what was said in Canvas. In this case, I'm going to assign late grades exactly what it says in Canvas. Okay, so if you're late by Canvas, it's late. So don't wait till the very last minute. Okay, and then it shouldn't be a problem. But and if for some reason there's some other huge deadline on Friday right around midnight, and you guys would rather if you do like later, that's fine. But you just need to let me know. That seemed like a good time that you have time to do it. It's before the final. Hopefully, we'll get it back before the final. That's kind of how that timing is set. All right, and there are some extra questions on homework 5 that are kind of meant to make up for the challenging aspects of quiz number 3. Those will be added onto that grade. I hope you will all do them because my objective is for you guys to learn this material, right? So I think a lot of you have been doing pretty well in this course. I think a lot of you have been learning a lot. So I think this will really give you hopefully you've got a good understanding roughly of what this kind of data analysis field is and get a sense of the notation in mathematics, and we'll be prepared to take the next courses in the sequence. So, all right, so that was kind of my little spiel. Hey, anything else? Administrative questions before I dive into the lecture? Quiz 4 will be the end of the lecture today. That's why so many people are here. And so I'll hand them out by 3:50. If I'm kind of rambling on and it looks like I'm not watching my watch, please let me know. Okay, great. So today we're planning to finish up some stuff on classification. Okay, and so again, just like before, the input is now a set of labeled points. So X is R and D. You can think of it as a matrix of n rows in D dimensions, and Y is going to be these labels. And again, n of them correspond here. Okay, and so the basic thing is we've been learning a function g which goes from x to the reals, and we want that the sign of g of xi to roughly or general max the sign of yi, right? So this is what the classifier was. And so we're learning this continuous function, but then we pick essentially some threshold between, say, positive or negative, and that allows us to make a prediction on the sign of this y value here. And this is our data. We want a general function, which when we see new data, this will work as a good guess of what the label will be when we don't have the label, right? And so far, we've learned these linear classifiers. And so this basically had g of xi was equal to some dot product with some alpha here, right? Where it was just a linear function here. And then we learned these these kernel classifiers, and this is more complicated. We want to replace this with the kernel, but we need to do it over these weights instead. And so it looked like, and we only needed one weight per data point. In general, if there are infinite number of data points, you need a number. And so this would be times some kernel xi of, or now it's here, let's use j here. This was xi and xj, right? So now we can, in order to do the kernel, we couldn't accumulate everything into this weight vector. This was like the w before. We couldn't accumulate everything in here. We need to expand this out into a kernel. This kind of still had a very similar flavor, and we could still either run perceptron or do gradient descent on this. What I want to talk about today are kind of quickly two other classes of classifiers. There are a huge number of different classifiers. The machine learning class will talk about even more of these. First, let me just say k-nearest neighbor classifier. What this does is basically you have these labeled points and these unlabeled points. Now I want to pose a question of right here, is this point, so is this point right here, is this going to be a plus or a minus? And what I would do is I would choose the k closest neighbors, right? So this would be a 3 nearest neighbors. I return everything within the set, and then I vote. I will take k usually to be odd. That way voting, I don't have any ties. Right, I look at 3 closest neighbors, the 3 closest points. 2 of them are positive, 1's negative, so I'm going to vote for positive. Okay, so basically, this is a completely different function, right, of some query point, let's call this Q, is going to be the majority sign of the 3 nearest neighbors of P, or of Q. Right, so this 3 nearest neighbor function is like this nearest neighbor function we use for clustering. Right, this was kind of like this Q, I have this data set X, where I have this return the nearest neighbor. But now it's going to return the k nearest neighbors. Right, so now is going to return the x1 up to xk subset x that are the k nearest points to Q. Okay, so I'm instead of return just the closest point, I'm return the k nearest point. I'll look at the sign of all these points and I'll vote. Right, so this is a completely different sort of classifier. It's still building a function, right? This is a function that I can think of a function as an algorithm, right? But it's some prefixed algorithm for any input value Q, any point, it will return a sign. And that's my classifier. Right, it'll return minus or plus. Yeah.
This k has to be odd because otherwise you have ties.
Yeah, right. So I said generally you pick k as odd. You know, sometimes you might want to actually return, say, you know, I'm not so sure. And maybe you return -1, +1, or 0 if you don't know. And you could then kind of have a loss function that scores that in a way that's separate if you want to. But generally, you just want to pick k as some odd number. 3 is a good choice. 5 or 9 might be reasonable as well. Yeah. Okay, so this is also a classifier completely different than what we did before. this sometimes works really well, you know, when these other ones don't work very well. But then there's not really a compact representation of this function. I need to do this nearest neighbor thing, and even with k equals 1, remember in high dimensions this could be, there's not really an efficient algorithm for this. I mentioned with in the Voronoi diagram function. And the complexity of describing this can be kind of hard. So but there are data structures that allow you to maybe do this fast. Okay. Okay, so that's one thing. Another one that you've hopefully another one you probably heard of are these like neural nets. Okay, and so deep learning is basically generally kind of an extension of these neural nets. Okay, and so it's a pretty old classifier algorithm. It's meant to kind of mimic how neurons work in the brain. Okay, and so how this works is you think you have an input. Input x is going to be some point in Rd, and I'm going to write x1, x2, x3 up to the coordinate xd. So these are the coordinates of this vector x. But I'm going to treat these coordinates kind of so as a so kind of in a way where I mean, think of they have different values with them, and I want to kind of weight the importance of each of these. So I'll weight 1, weight 2, weight 3, weight d. And so these are going to go, and I'm going to add these all together, right? So think of, these are different kind of possible stimuli you're seeing in your eye. It has different sensors in it. If it sees kind of a big thing of light in this thing, it sends it and it accumulates inside the neuron. It adds together all these weighted contributions. The weights could be negative, that's fine. But then it outputs it, typically it wants to output so -1 or +1. It doesn't directly usually, so if I just want to say, or if it's, so if I just want to check if it's -1 or +1, what I would check is if there's a function where it's -1 if it's greater or equal to b, or it's say +1 and it's -1 if less than b. So I can choose then some offset here, right? So some bias term here. Okay, and I could set b equals to 0. So then it's just the sign of the sum, and some of the weights can be negative. Okay, so what is it actually going on here? This is actually the same thing as x times it's exactly this function. It's a dot product between the vector x and this accumulation of the weights into a vector w. Okay, and then I have some offset here. Okay, so one neuron in a neural network is exactly a linear classifier. It's exactly the kind of what the perceptron is trying to do. And if you think of how you actually might learn in practice, is that if you get negative feedback from something, then you'll fire along this weight and you'll add it to this, right? So if I see an example which is misclassified, a neuron fires and it updates my classifier weights. And so that's kind of where the perceptron came from intuitively. I'm learning W by adding, the instances of these weights, kind of one by one. Right? So it's kind of linked back to the perceptron came from this sort of thinking, actually. Is there a question?
The weights are chosen randomly, right? You initialize it, or do you have like guaranteed
Well, so I mean, at this point, the goal in the model is to learn the weights, right? So I could initialize them randomly. I could initialize them to 0, which is what I do in the perceptron, right? Yeah, inside a big neural network, it might be good to initialize them randomly in some range. It might be, but often, in practice, often if you're using a network, you want to kind of use some kind of preconditioning on it, and then you might kind of learn some initial weights that way instead of starting from scratch. Okay, so this is one neuron, and so if this is like one structure here, then what a neural network is kind of a set of these structures. Okay, so it's going to be I'm going to have x1 through xd, and then I'm going to have these structures so I'm going to learn different weights for each of these. Okay, so I'm going to call let's call this one W1, W2, up to WK. And I'm going to stick I'm going to learn K different of these. And what I'm going to get as the output here is going to be a new vector. Z, and this is going to be in RK. Okay, now this is not quite right. Actually, this vector, as I've described it, is going to just be kind of, it might just be signs here. I don't want it to just be signs. I want it to be a continuous value. So I'm going to add, on the end of every one of these things, this, so this activation function phi, and basically this is going to map from the real numbers basically usually to 0, 1. It could be, or to, it might be to -1, 1, or to, let's say in some cases, 0 to infinity. Right, so it's going to, I want this to kind of act kind of like a binary thing, but I'm going to need to take a gradient at some point. So instead of this kind of binary function, I need something that I can take the derivative of it that looks like a binary function. Okay, and I'm going to put each of these on the end here, which is going to, I'm going to activate these, and so then each of these is going to be some value z1, z2, up to zk, and these are going to be real values in here, but they're going to be, depending on the input, they might be pretty close to, say if it's between -1 and 1, it might be pretty close to 1 or -1. So these are kind of like events, like it's true or not true, but it's going to be smoother than that. And then and so this one version of a neural net, I can solve this optimally basically with the perceptron. But what I get, the real power in deep learning is I'm going to stack a bunch of these together. Right, so I'm going to get this next layer here, and then I'm going to have all these connections in these layers. I'm going to chain a bunch of these layers together, and then eventually I'm going to predict -1 or +1. And there are ways to extend this to multi-class, which we're not covering here. Yeah.
So I guess I think my confusion. So this how part is just one perceptron basically Is that right?
Correct,
And
yeah.
and then right here, down here, we're kind of overlaying many perceptrons.
Yeah, so we're doing two things. This layer is a bunch of individual perceptrons, right? That gets to values in the next layer. And then I'm going to do that again, and that's one layer is a bunch of individual perceptrons.
So I guess what I'm confused about is if, like, it seems like if we had a bunch of perceptrons, they would all just, if we tried to solve the same problem with all the same perceptrons, it seems like they'd end up with all the same weights.
If I just did one, yeah, right. And I was doing binary classification. So if I'm just doing one, I only need one perceptron, right? If I'm doing two layers now I can learn. So there are a couple things that happen when you do two layers. One, this is not convex anymore. It's no longer a convex problem. And I can end up learning things that, like in OR, of different, I'm doing two layers. When I had one linear classifier, I could have that. This was basically my, was like my G function was essentially one linear function gave me a line. But now I can do something this can be W1. This is W2. This is W3. And I get like in 4 of these. And now I can define the positive as this internal region, or maybe the AND of these. I can do ANDs or ORs. And this is the negative region out here. Right? So I can put a bunch of these together, and then this allows me to learn a very different, more powerful shape than I can with the single linear classifier. Right? And so basically think of each of these as one of these initial neurons. Gives me a different kind of linear classifier. And then the next layer allows me to glue these linear classifiers together. Right? And then if I have more layers, I can do more complex things than this. Right? Yeah.
When you pass it from one layer into a next layer, is that the same thing as like a feature transformation?
Yep. Right. Okay. Yep. So you're asking lots of questions about this. Well, let me kind of just got a sequence plan, and we'll get to some of these things.
Sorry.
Okay. Sure. Okay. So now I'm going to stick a bunch of these together, and what's going to happen is each of these W's is going to be a vector, a d-dimensional vector, and I'm going to get this matrix W1, which is W lowercase w1, what's it called, 1, 1, k. Right, so now this is a matrix that goes from maybe it should be the transpose of this, okay? But it should go from D to K. So I'm taking a d-dimensional vector, I transform it into a k-dimensional vector. So I can write each of these dot products now as a row or a column of a matrix, and it does a transformation using a matrix multiplication. Right? And so I get W1 here, I get W2 here, W3, and so on. So I can write all these layers together. Okay? And what happens ultimately is that I'm going to get out of it this function g of x, which is going to be, what's happening is I'm going to get x times w1, but then I have this activation function 1, which is I apply this usually the same thing on each of the outputs. And then I take the output there, and I multiply that. I do another transformation by W2, and I apply an activation function on W2. And eventually, I get an activation function WL, and I apply this matrix on the output here. Okay, so my overall function is this kind of string of some matrix, then a fixed activation function I've chosen, another matrix, a fixed activation function, and so on. I can chain these all together. Okay, so the parameters, right? So we had this alpha describe the parameters that we learn. It's going to essentially be the union over L equals 1 up to L of the Wij, right? So it's all of the values of all the matrices. So I have big L of these different transformation matrices, and they each have, say, D times K or K1 times K2 parameters. So there's a huge number of parameters here. The size of alpha might be L times K squared, right, of these parameters. If each matrix is K by K, I have this many different parameters to learn here. So it's a huge complex system, right? With linear classifiers, for d-dimensional vectors, I have d parameters, or maybe d plus 1 parameters to learn. Now I'm basically looking d squared times L for L layers, huge number of parameters, okay? Also, so G, I can write it, G of alpha of X, I can write this as the sum over G of the overall. So I can rewrite this as a function f of I of alpha, and then I have an overall function f of alpha. Okay, so the overall function is still, I can learn, this is not, right. So the cost, the loss, right, so the loss I can still write as kind of the sine times this g of alpha function, or right, as some sort of output here. And this function is still decomposable, right? So I can still decompose the overall cost function. The overall cost function I'm trying to optimize is still decomposable into pieces. And so you could think, okay, now I can run gradient descent or stochastic gradient descent on F, right? It has all these parameters, a huge number of parameters, but it's a function, so I can run. So really, you want to run gradient descent, or actually stochastic gradient descent on F of alpha, but it's not convex. Okay, so the big concern, and like one of the reasons that kind of work in neural networks paused for a long time is people are concerned everything else we do with linear classifiers and these kernel classifiers, they came to these convex functions, and we knew if we ran gradient descent or later on stochastic gradient descent on them, they would converge to the kind of the optimal alpha for the loss function we have. These now have a huge number of parameters, so maybe they're overfitting the data, and this is not convex anymore. Okay, but it turns out, we can compute the derivative. Right, f alpha. Right, so I can pick some parameter value, and I can compute the derivative for a single data point. So I can still compute the derivative. This is through a technique called back propagation. Okay, so I can still compute the derivative. And people said, okay, well, let's still run gradient descent. It might get stuck in a local minimum. but I can, but let's see how well it works. And if it doesn't work very well, I'll randomly restart my guess of what the alpha parameters are, re-randomize those values, and try again. And this, with ways of doing backpropagation and this at scale, this has become very popular and has worked very well, very powerful. And somewhat surprisingly, it doesn't tend to overfit. You actually, even without a lot of explicit regularization in here, you tend not to overfit on data if your data set is really, really big. So I wouldn't run this unless you have a really huge data set, but if you do, this can generate the most powerful, the most kind of best at generalizing to new data classifiers, from today. Okay, there are a few more points I wanted to hit, but there a question? Okay, good. So I haven't explained. Let's see, I skipped over a couple things here. So the activation function. So an example activation function. Let me just. So. Okay, so so the most common activation functions are probably the sigmoid, which goes from equals 1 over 1 minus e to the minus z, which is equal to. And so basically what this looks like is I've got these real values, z, and here's 0, and I want this to map, the output of this was, this one maps between 0 and 1, and it looks something like this. Okay, so this is a smooth function that has a derivative. Things that are very small, it tends to map to 0. Things that are very large, it tends to map to 1. And things in between, it kind of smoothly transitions. So I'd like to do a sine function where this is 1 and this is minus 1. But I want to take a derivative, and this allows me to take a derivative here. And another common one is the ReLU, the rectified linear unit, and this is equal to the max of 0 and z. So this looks like right. So it's linear. It's linear afterwards here. So the derivative is simple here, and it's 0 before here. So if I have something that's correctly classified or has a 0 value, then it has no derivative, and it has the derivative here is, I can basically just ignore it. The derivative is 1, right, everywhere here. So either I do the derivative calculation, or I can ignore it because it's below 0, so it had no effect. And so this one is going to be more efficient because, one, the derivative is easy, and here the derivative, there's no derivative, so I can kind of take it out of the calculations I need to do in backpropagation. Okay, so these are functions I can basically take derivatives of that I stick at the output of each of these dot product perceptrons. And so I kind of am doing something like I'm rounding kind of like to 0, 1 here, or but it's smooth in that I can take the derivative of. Okay, 2 more things I want to say, and I should say we're nowhere near covering everything about deep learning. There's a lot of software out there that makes this a lot easier now. There are classes that somewhere are being taught. I don't think we have one next spring, but We've had one the last few falls just on deep learning, and there's either a computer vision class, which is very deep learning heavy, or just a deep learning class. The deep learning for NLP classes. There are lots of specific stuff in here that's beyond just kind of thinking about machine learning. Okay, so I'm just trying to give you a big idea of what's going on given the notation and machinery we have in this class. Okay, so how do we think about this? In the previous with kernels, we were doing something where we said, well, I kind of want to build a linear classifier at the end. The very last step here will be like a linear classifier. Usually will be something like that, okay? But I want to kind of think about transforming it to a space where that linear classifier makes sense. So I somehow need to featureize the data, and then so it's linearly separable. And so you can think of the first several layers of the neural net as being kind of defining what those features are, and the last layer is just a linear classifier on top of those features. Okay, and so how machine learning had been a lot of the activity in it, especially in industry up until deep learning took off, was there was a lot of hand tuning of these features. People, either they use kernel methods, which is kind of a mathematically kind of a proper way of doing it, which kind of gave you these more powerful family of features you knew you could run gradient descent on, or they would hand tune these things. They would take images and look at these windows on images, and that would generate features, or in natural language processing, there are other sort of things they did. What deep learning is doing is it's saying, I'm putting these features as part of what I'm learning. So I'm not only learning the best parameters of the linear classifier at the end, but I'm learning the feature values as well. And by throwing it into a single big system somehow, I can kind of learn the parameters of the features, and these are better than any hand-tuned features. So the first several layers are essentially featureizing the data, and then the next ones are learning some complex kind of transformation. And then the last one is a linear classifier. Okay. The other thing that goes on is usually when you look at these really deep architectures that are 20 or 100 layers, I don't have it fully connected. I don't have it fully connected every layer. I only do that on maybe the first couple layers and usually the last layer. But in between, I'm usually doing something structured in some way. And this really becomes like an engineering problem. Instead of choosing which kernel to use, I'm choosing how to structure the internal layers of the network. So that means that these matrices, they're not mapping from everything here to everything here. I'm mixing each of these edges. I might not include some of the edges here in some way, or I might add some structure in between. Okay, and so a lot of what goes into actually engineering a good deep learning system is choosing the architecture, which is choosing how the connections go between the layers and having the layers mean something. They may shrink down to a small layer and then go back up to a big layer, and that's a way of kind of forcing all the information to go through a small number of parameters and some vectorization. And there's a lot that is going into that. Okay, so there's a lot of engineering that goes on there, but that can be, you can do that more easily now. There are these nice interfaces for doing that. Yeah.
So where it says on the left side of the blue box where it says X1 and XB on the bottom,
Yeah.
Does that mean that we're only doing one X at a time, one data?
Yeah, this is a function. This is a function, where did I write it? G, that takes in one data point and gives, and I take the sign of this at the end to, in order to make a prediction. Right? That's the same way it works before. It's still a single function G, and I just want to eventually take the kind of, that's a single predictor for a new data point. Okay. Right? So now this could be, for instance, an image classification. These are all the pixels of an image, right? All the pixel values of an image, right? So this could be a pretty long vector here. And then the first layers are going to maybe not fully connected. They are like these convolution features. So each one of these red ones might only be looking at a subset of the elements, which defines some neighborhood of the image. Right, so that's kind of some of the structure that this architecture can have in that you need to engineer based on what your data looks like. With natural language processing, often you'll take a sentence and then for each word in that sentence, there are these pre-trained layers, either these word vectors like word2vec and GloVe you may have heard of, or now these actually more dynamic layers where they learn some kind of function that takes more than just an individual word, and that maps that to some vectorization. But then you do that for all the words, and then there's another layer that combines these together in some way and looks at the structure of the sentence. And there's a lot that goes into architecting the structure. Yeah.
So on the first layer, let's say you're doing, for example, an image. One big thing about an image is that you have basic dimensions. So when it comes to an image, is learning which pixels are adjacent to which just something that happens through teaching process?
No, that's usually structure given in. You know it's like 256 by 512 or something for an image, and you vectorize them, but you keep track of which ones are near each other. So you build these filters that kind of moves over every window of a certain size when it's a rectangle, right? And so these know which ones are next to each other.
Okay.
So that's architected into it. So again, so it's not completely a black box. You still need to kind of design how you build the learning that way. Yeah. But then you can learn the parameters of what that function does, is what deep learning does for you. Okay, I may will say something else about backpropagation, just briefly, and then I'll end up the quiz. You can compute this actually really efficiently. Why this is work is that you can use the chain rule to actually compute all the parameters, starting with the parameters for the last layer, and then the next layer are a function of those parameters. And otherwise, the gradient is this huge, kind of this alpha is so big, it's be really hard to learn all these, but there's an efficient way to do it kind of without kind of looking at the whole joint process. You can look at it layer by layer. And this efficiency is what's allowed it to be scalable. Again, I don't have time to go into that, but hopefully this gives you a taste of why there's a lot more to learn out there. Okay, great. So let's end there, and I'll end up the quiz. So please put away laptops, phones, calculators, and you can have out your scrap sheets. I'd rather all that electronic stuff is